This is and our goal today is to start Interannotator agreement, which is another nice application of probability, and also go back to what we were discussing in hypothesis testing, the fact that there are two types of error, type 1 and type 2. And we want to show that there is an intimate connection between interannotator agreement and hypothesis testing. Okay, so this connecting these two dots, that is interannotator agreement and hypothesis testing, is pretty interesting. Okay, so let's directly jump into interannotator agreement, and in that also a very frequently used measure which is called Cohen-Kappa. We are directly going into a matter of detail, and we'll come back to philosophical issues and broad picture and big picture of what is interannotator agreement, what is the meaning of agreement in the context of reliability, data, statistics, and so on. Now, Cohen-Kappa is a quantitative measure of reliability for two raters that are rating the same thing. And that measurement is corrected for how often the raters may agree by chance. Okay, so the moot point is this: how many times they can agree by chance, and we have to correct our quantification for that agreement by chance. The value of kappa is -1 to +1. And the original paper of Cohen, who was a psychologist, interestingly, and the paper which introduced Cohen's kappa came out in 1960. Okay, long back, about 60 years back. So that says that the square of the Cohen kappa is a very nice measure of agreement between two raters. Now, this getting something rated by multiple raters is a frequently occurring situation. So we'll go to NLP and think of an annotation scenario. Consider an annotation scenario. And the problem is sarcasm. So text is given to annotators, and they have to rate if the text given is sarcastic or not. And we know from our experience that sarcastic data is relatively small in percentage of the amount of text that is available with sentiment annotation. So we have taken two annotators, A1 and A2, and we have given them 19 sentences to say yes or no, depending on whether the sentence is sarcastic or not. Okay, there are 19 sentences. So that is reflective of the fact that the sarcasm data is pretty scarce. Now, here is the annotation statistics. We have recorded the annotator's annotation on the data. Now, let's say I take A1, the first annotator. So annotator has said yes for 10 documents and no for 3. That is, 10 sentences are given the rating yes. And 10 plus 3, 13 sentences are rated yes by A1. And 10 plus 4, 14 sentences are rated yes by annotator 2. And similarly for A1, the number of no's is 6. For A2, number of no's is 5. Okay, so this is the cold data. And we have also noted how many times A1 and A2 agree in terms of yes and in terms of no. So A1 and A2 agree for 10 sentences saying yes, and they agree for 2 sentences saying no. And there are 4 cases where annotator 2 says yes, but annotator 1 says no. And similarly, 3 cases, annotator 1 says yes, annotator 2 says no. Okay, so this is also called a kind of contingency table, where the ratings by the 2 annotators are depicted as a matrix. And you can surely visualize that when the number of annotators becomes more than 2, we'll have an n-dimensional entity with different cells marked as yes or no, and we can obtain this this value of the counts for a tuple A1, A2 up to AN. Okay, so this is the scenario, and now let's see what we can do with this data. So the calculation towards Cohen-Kappa follow the following steps. Okay, so first of all, we calculate the probability of observed agreement, and this is given the notation PO. So the number of times, total number of sentences is 19. For 10 sentences and 2 sentences, the 2 annotators A1 and A2 agree. Okay, so they agree saying yes for 10 sentences, and for 2 sentences they agree saying no. So 10 plus 2 is 12. 12 by 19 we say is the probability of agreement. Okay, this is 0.63, and that's a pretty good value. But there is a headache here. There is a thorn in the flesh. We also have to correct for the probability of chance agreement. So both these probabilities will have to match with our fundamentals of probability theory. Okay, and see why we can calculate the probabilities the way we are doing. Okay, so 10 plus 2 is agreement of yes and agreement of no. So agreement of yes and agreement of no are mutually exclusive events. Okay, so we can sum these. So this is 10 by 19 plus 2 by 19. So we are actually summing 2 probabilities, and these 2 probabilities are mutually exclusive. Okay, and therefore we are able to sum them. But what is the random variable? Okay, and how are we obtaining this 0.63? We'll work them out starting from fundamental observations of probability. Now we come to probability of chance agreement. Okay, now probability of chance agreement is little more complex, and it will need looking at the structures of probability theory a bit more closely. So probability of chance agreement, you see, is depicted as 13 by 19 into 14 by 19 plus 6 by 19 into 5 by 19, which comes out to be 0.58. So this is more than 0.5, and it is a matter of worry, because the probability of chance agreement is more than 50%. Okay, so that's a pretty high value, and therefore the data that we have collected is not to be trusted completely with respect to the agreement of the 2 annotators. Okay, why so? So we'll come back to this formula once again. Now the Cohen-Kappa is calculated by this formula, and if you go to Microsoft Excel and if you go to the internet, there are packages for calculating Cohen-Kappa using this formula. So Cohen-Kappa calculation, measuring interannotator agreement is a pretty mechanical process, but the probability theory behind that process is really interesting, and we will move forward to look at those underpinnings. So probability of observed probability minus probability of chance agreement divided by 1 minus probability of chance agreement gives me a value of 0.63 minus 0.58 divided by 1 minus 0.58, which is 0.12. So we got an impression that the two annotators have fairly good agreement, and therefore we can trust their we can trust the judgment that we have obtained. Okay, so there are 19 sentences, and we have given them to two annotators. We know that sarcasm is a difficult phenomenon. It is difficult for human beings to spot sarcasm. It requires a fairly high level of intelligence, requires a fairly high level of domain expertise, and also fairly high level of linguistic expertise. So spotting sarcasm and generating sarcasm, producing a sarcastic sentence, are non-trivial language and cognitive abilities. Therefore, whenever we obtain sarcasm annotation on data, it is never a good idea to rely on a single annotator. The nature of the problem is complex, and it demands that multiple opinions are taken. So now in this case, we on the on the first go, when we looked at the data, the first impression was that the two annotators have a fairly good agreement, and therefore their annotation can be trusted. But when we go and do correction for the probability of chance agreement, then this comes down drastically from 0.63 to 0.12. Okay, and how good or bad is 0.12? So this is seen if you do a bit of Google search, then this kind of table can be seen. If the value of kappa is between 0.4 and 0.59, the level of agreement is weak. And the percent of data that are reliable is only 15 to 35%. If the value of kappa is 0.6 to 0.79, the level of agreement is moderate, and 35 to 63% of the data is reliable. 0.8 to 0.9, strong agreement. 64 to 81% of the data is reliable. Above 90% is almost perfect. So that is giving rise to the situation of 82 to 100% of the data being reliable. Now, all this level of agreement, the data being reliable, okay, these are qualitative observations. I mean, they are numbers, but you see these observations: weak, moderate, strong, almost perfect. These are qualitative judgments, okay, and decision makers always go by this kind of qualitative judgment, and the underlying these qualitative observations are numbers, which again need to be scrutinized, and they should be trusted after this scrutiny is over. So now if I go back, then I do see that 10 by 19 is a probability. What is this probability? The probability of the probability of agreement, okay, the probability of agreement being yes for both R1 and R2. Now you begin to see some subtleties. Okay, the probability of 10 by 19, this quantity, this cell here, is the agreement cell for both R1 and R2, or A1 and A2. Okay, so A1 and A2 agree, saying that the sentence is sarcastic 10 times out of 19. Okay, and then there is this cell here, which is 2. This is the cell of agreement between the two annotators when they say no. Okay, and both saying yes and both saying no cannot have any intersection area. So these are mutually exclusive events, and therefore they are added. Now I come to this formula, probability of chance agreement. So 13 by 19 is the probability that annotator 1, okay, A1 should have been A1, says yes. Okay, 13 out of 19 cases, the annotator 1 says yes. And 14 out of 19 cases, annotator 2 says yes. Okay, so these two probabilities are multiplied, plus annotator says yes, uh, 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 annotator 1 says no 6 times out of 19, annotator 2 says no 5 times out of 19. Again, these two probabilities are multiplied. Okay, and these two probabilities are after that added. Okay, so what laws of probability are operative here? Okay, we can multiply two probabilities when the two events are independent. Okay, so this is the measure of joint probability of annotator 1 and annotator 2 saying yes independent of each other, plus annotator 1 and annotator 2 saying no. Okay, the probability of that happening independent of each other. And these two joint probabilities again are mutually exclusive, and they are being added. Okay, now what is the theory behind subtracting PE from PO, and what is the theory behind 1 minus PE? Okay, what is the theoretical foundation after all for this kind of calculation? So this we will dig deep into. Okay, we'll dig deep into this. So let's proceed for some intermediate instruments that we need. Okay, so we need the concept of contingency table. Contingency tables represent categorical data, and they study the influence of two attributes on each other. And are the attributes independent of each other based on the data is the question we ask. Okay, so now Ankush asks if the kappa score is less than 0.4, is the reliability of the data low? Yes, it is low. If you go by this this table, it is low. Now in our case, we found that the kappa score was 0.2. Therefore, the reliability of the data of the annotation is really very low. Okay, really very low. Okay, so we will take up these discussions as we go forward. If not today, then in the next lecture. So we are discussing Cohen kappa, and we need the concept of what is the logic. There was a question. I'll look at these questions a little later. Okay, so study influence of the two attributes, and are the attributes independent of each other? So now here is an interesting example situation. We have made a study of smoking habit of a set of students, males and females. And this is the data which we have observed. Male smokers are 72 in number. Male non-smokers are 44. So total number of males is 116. Female smokers are 34. Female non-smokers are 53. Total number of females is 87. So this is the row sum. If we look at the column, then the number of smokers, male or female, is 106. The number of non-smokers is 97. Okay. So now let's look at some naive conclusions that can be drawn. And we are surprised by the number of times these kind of conclusions are drawn. So for example, since the number of male smokers is 72 and number of female smokers is 34, then sometimes the conclusion that is drawn is smoking is more common amongst males. Okay, that may be true, but we have to apply principled framework to come to this conclusion. And we have been doing hypothesis testing, chi-square testing, z-test, and so on. So we have developed some amount of capability. We have some instruments to give a principled judgment on whether number of male smokers is more than number of female smokers. Then again, if I look at the data, I see 106 smokers and 97 non-smoker. So can I say that in the population, okay, in the population, the number of smokers and number of non-smokers are evenly distributed. They are more or less same. Okay, the percentage of smokers and percentage of non-smokers are approximately same. So all this is based on sample, and we are making these conclusions about the population. Okay, now how principled are these? After these 16 17 lectures, we should be making a more scientific approach. We should be taking a more scientific approach to answering these questions. But by looking at this table, you can begin to ask these kind of questions. The most interesting question, of course, is are the number of male smokers more than number of female smokers? Okay, then of course you'll have to form a null hypothesis, and you'll have an alternative hypothesis. You'll have to match the data with the null hypothesis, see the error region, fix the confidence interval a priori. Okay, all those things that you have been doing so far are relevant. But what is the relevance of this kind of hypothesis testing to interannotator agreement? Okay, that is our cardinal question today. So now this is called the frequency table, from which I can get the total number of males, total number of females, total number of smokers, total number of non-smokers, and the intersection of these attributes also. Okay. So a very useful operation that is performed is going from absolute frequency table to relative frequency table, which takes us to probability. So the total number of students surveyed is 203, 106 smokers, 97 non-smokers, 116 males, 87 females. Now I can begin to see the interaction of these two attributes, okay, smoking habit and gender. So I look at these individual cells. This first cell is the cell of gender being male and habit being smoking. So this is 72 in absolute terms. So what is the relative frequency? We take 72 by 203 and multiply it by 100. So this is 35.47. So what is the meaning of this? This says that 35.47% of the population are male and smoker. Okay, why can we say this? We can say this because of the maximum likelihood principle. Okay, if I am asked to give a probabilistic estimate of what is the probability that an individual is male and a smoker, okay, randomly drawn individual from the population is male and smoker, that probability is 0.35. Okay, and this is a fairly principled statement. Okay, given the data, this is the best you can say. You cannot do better than this. Okay, this is according to the maximum likelihood principle. Now 35% of the population is male and smoker, 21% is male and non-smoker, 16% female and smoker, 26% female and non-smoker. Okay, and 57% of the population is male, is female, and that gives me 100%. So this is the way we obtain the relative frequency table, which is again a very important step towards all these discussions. Okay, remember, I'm reminding you, we are trying to connect the two dots of interannotator agreement and hypothesis testing. Okay, and it will be very interesting for you to see how at the base of everything there is a null hypothesis, okay, which we are not stating, but which is there. And the consequence of that null hypothesis is being manifested in everything that we are doing going forward. Okay, so remember, we are trying to connect these two concepts, and here we are trying to see how to correct for chance agreement. Okay, we are trying to also understand how we are calculating the chance agreement and why this subtraction from observed probability, why this subtraction from 1. Okay, all these probabilistic steps we are trying to understand in terms of probability theory. Okay, so that's interesting and it's quite empowering also. So at this point, we would like to bring in chi-square test and the contingency table. So I take another example. Maybe I should have always stuck to one example and discussed all these concepts, but that is okay. We'll do something about that later. So here is again some data about gender versus political leaning in the American setting. So we have surveyed a population, a sample of 100 people, and we find that the number of male Republicans out of this sample is 26. Male Democrats is 13, and others are 5. Okay, so total number of males surveyed is 44. Female Republicans 20, female Democrats 29, female others is 56. So we are trying to draw conclusions about the influence of gender on political leaning. Can we say that males are mainly Republicans? Okay, because 26 is more than 20. But we know, after all these lectures that will be very naive and incorrect also. So total number of people surveyed is 100, and this is the row total and column total. Okay, so this is the data, and let's see what we do with this data. First and foremost, we get these expected frequencies. The observed frequencies are this: male Republican 26, male Democrat 13, and so on. We have to get the expected frequency as per the theory of chi-square test. Okay, you remember we have done chi-square test before, and this will be a kind of revision. So total number of expected male Republicans is calculated this way. 44 divided by 100 into 46 divided by 100 into 100, which is coming out to be 20.24. Now, what is this quantity? Okay, what is 46? What is 44? So total number of males is 44. Total number of Republicans is 46. Okay, total number of males 44. Total number of Republicans 46. So effectively, we are multiplying 44 by 40 into 46 and dividing this by 100. So 44 by 100 into 46 by 100 into 100, 100 will cancel, and therefore we will have total number of Republicans into total number of males divided by the total population size, which is coming out to be 20.24. Now arises a very interesting question as to what is the theory behind this kind of calculation. Okay, and this is where, interestingly, you will see the importance of null hypothesis and how at the back of your mind, subtly, very subtly, the null hypothesis is operating. So how are we calculating the expected frequency? Are the slides visible? Can somebody testify?
Yes, sir.
Yes.
Okay. Okay. So how are we calculating the expected frequency? Are we right in doing the calculation this way? So expected number of male Republicans is probability of male Republicans into total population. That is by definition of expectation. Probability of male Republican into total population. And that is equal to probability of male into probability of Republican into total. Here, somebody will raise a finger and say that, sir, you are doing something without explaining your stand. Probability of male Republican is probability of male into probability of Republican. How can you multiply these two probabilities? Okay, because your male Republican, the random variable that a person is male and the random variable that the person is Republican, these two random variables, are they independent? Now you go back to the problem statement. The problem statement was, we are trying to understand the influence of gender on political leaning. Okay, we want to understand the influence of gender on political leaning. We want to understand whether these two attributes influence each other. And then you see, if I multiply these two probabilities, then I am assuming that gender and political leaning are independent of each other. Okay, so we'll come back to this point. So probability of being male is total number of males divided by total number of the sample size, which is 44 by 100. This is by maximum likelihood principle, remember that. And probability of Republican is number of Republican divided by sample size, which is 46 by 100. And total population size is 100. So as per the definition of expectation, I have calculated this quantity. So this will be total number of males into total number of Republicans divided by to a population sample size. Okay. Now comes the this point about multiplying these two probabilities. Why are we able to calculate the expected frequency this way? We would like to recall our knowledge of hypothesis testing, especially the null hypothesis. So remember the original problem statement, does gender have any influence on political leaning? On, not off, on political leaning. So the two categorical attributes, are they independent of each other? For the sake of calculation and for proceeding forward, let's assume this, that the two attributes are independent of each other. Gender has no influence of political leaning. This becomes my null hypothesis. So attribute gender and attribute political leaning are independent of each other. And the alternative hypothesis consequently is that the above attributes are dependent on each other. Okay, so on each other. So it is because of H0 that we are able to calculate the expected frequencies. Okay, so this point you have to appreciate. Okay, we have started examining this question, a very nice political sociological question. Does gender have any influence of political leaning? The earlier question also was interesting. Are male is smoking more frequently found in males? Again, an interesting social question. Okay, what has it got to do with two annotators deciding if a sentence is sarcastic or not? Two annotators deciding if the sentence is supporting Republicans or Democrats. What has it got to do? That interesting connection will establish through the discussion on contingency table and this method of hypothesis testing through chi-square test. Okay, so let's proceed. So again, since I personally find it very thrilling, I draw your attention to the this practice of first establishing the null hypothesis and then proceeding based on the null hypothesis. It is the null hypothesis which is allowing me to proceed with the data and making calculations on the data. If the null hypothesis was not there in the backdrop, I will not be able to make any progress. Okay, so I take the null hypothesis, go forward, and see what is the consequence. If that invalidates the data, then I'll throw away the null hypothesis. If the data is consistent with the null hypothesis, then I cannot reject the null hypothesis. So let's proceed. Okay. Okay. So I'll come back to your questions. I see some of them in the chat box. So gender versus political leaning, the expected frequencies are now recorded. Male Republican frequency, expected frequency is 20.24. Male Democrat 18.48, male others 5.28, female Republican 25.76, Democrat 23.52, others 6.72. So at this point, it will be interesting to compare with the actual observed frequency. So actual observed frequency for male Republican is 26, expected is 20.24. Male Democrat 13 observed, expected 18.48. Male others observed 5, expected 5.28. Female Republican observed 20, expected 25.76. Female Democrat observed 29, expected 23.52. Female others observed 7, expected 6.72. So there is oscillation. Sometimes expected is less, sometimes expected is more. So how can we draw a conclusion? Fortunately, we are on a strong ground on that front. We have done chi-square test. So let's see. Does the data support the null hypothesis? Gender and political leaning are independent. We have to do chi-square test. Okay. So our null hypothesis was that they are independent. So we'll do chi-square test. So just recall that chi-square test is actually a random variable, which is sum of standard normal standard normal variable square. Okay, so chi-square random variable is sigma x1, x2, x3, and the squares x1 square plus x2 square, x square, etc. And each of them is a standard normal variable with mean 0 and standard deviation 1. Just like in z-test, in chi-square test also we have to a priori decide our level of significance. So we decide it to be 5%. Our confidence in, level should be 95%, and we are prepared to tolerate an error of at most 5%. Okay, so if I reject the null hypothesis, the error in that is desired to be at most 5%. Okay, so this error level we had discussed last time. So this is to be 5%. Now let's see. We need the observed chi-square, and observed chi-square is observed frequency minus expected frequency square divided by expected frequency and sum over all the data points. So in this particular case, the number of data points is 6, 2 genders, male and female, and 3 political leanings, Republic, Democrat, and others. So 6 of them. So when we perform this computation, observed minus expected square by expected summed over all data points, we get chi-square observed as 5.8, and chi-square critical is actually 5.99. Okay, so the degrees of freedom here is 2. Okay, 3 attributes, so 3 minus 1 is 2, multiplied by 2 genders, so 2 minus 1 is 1, so 1 into 2 is 2. So degree of freedom is 2, and for 5% confidence interval, the chi-square critical comes out to be 5.99. This can be seen from the chi-square table. So those are mechanical nitty-gritties which are easily obtainable. Now chi-square observed is less than chi-square critical, so we have not entered the error region, so we cannot reject the null hypothesis. The data is such that it does not allow us to reject the null hypothesis when the level of significance is 5%. Okay, 5%. So we are supposed to accept the null hypothesis, that is that gender and political leaning are independent of each other. They have nothing to do with each other. Okay, so now coming back to we'll finish in about 5 minutes time. Coming back to our annotation situation. Okay, and we'll take up this discussion more elaborately in the next lecture. So we come back to our situation of two raters rating sarcasm. Okay, this is the contingency table. Okay, this is a contingency table for the two annotators, 10, 2, 4, 3. Now, the probability of observed agreement is 0.63, but after correction, it drastically came down to 0.12. And the probability of chance agreement is also very high. That is 0.58. So here what is the null hypothesis which is operating? Okay, what is the null hypothesis that is operating? We are trying to eliminate the possibility of chance agreement. Isn't this very similar to the contingency table for political leaning and gender and smoking habit and gender? Okay, there is a similarity between these three problems. Two annotators giving decision on whether the text is sarcastic or not. Gender and smoking habit, gender and political leaning. These three problems have a similarity actually. Okay, in the last two problems, the later two problems, we are interested in finding if the two attributes influence each other. Okay, are they independent of each other? In calculating Cohen's kappa and correcting for the error of chance agreement, we are asking the opposite question. Okay, what is the probability that they have chance agreement? It is possible that they exchange notes. It is possible that they do not know each other. They are in completely two different locations. They cannot have any communication between them. So all these situations have to be considered. Okay, and you will see also a semblance of similarity with the mutual information. Okay, so where we take the joint probability and multiply the two individual probabilities, assuming that the two random events are independent of each other. Okay, and then compare the joint probability with the probability if they're assumed to be independent of each other. So there is a relationship between them. Okay, so there are many dots which you have to connect and build a complete picture. The joint probability, calculation of joint probability, assuming that the random variables are independent, calculating the probability when they are actually not independent, then the method of calculating correlation coefficient, contingency table, the influence of null hypothesis on two attributes, okay, and then calculation based on the assumption of null hypothesis. All these dots have to be joined together, and then we have related these two concepts very firmly: inter-annotator agreement and hypothesis testing. Okay, so going forward we'll do that, and there is a tremendous importance of these things, because in machine learning we have to do hypothesis testing, but machine learning cannot be done without data, and raw data is quite useless unless we are doing unsupervised learning. We need annotation on the data. There we have to see the influence of chance agreement. Okay, so we'll do that going forward. And today there are some questions. Let me take those questions. Chat box. So Ankush had asked, when kappa is less than 0.4, data reliability is weak. Yes, that is what we see from that table. Okay, 0.4 is actually weak agreement, and the data reliability is just about 35 to 50%. Yeah, 35 to 50%, I think. From Ritvik, is this logic can be extended to more than 100 iterations? Yes. So when we extend this to more than 100 iterations, that is called Fleiss kappa. Okay. So we'll have to Fleiss kappa, Kendall score. So all these measures of Interannotator agreement we'll do going forward systematically. But again, always going back to null hypothesis testing, and theory of probability. Then again, Ritvik, sir, this hypothesis of do males smoke more often than females is based on an assumption that the samples were taken at random, isn't it? Yes, of course, of course. So this will surely depend on the quality of sampling. And we have done before different observations on what should be the sample size. If the sample size is more than 30, then we can make assumptions of normal distribution and draw from the theory of normal distribution, especially standard normal distribution, perform Z test also. Okay, so these were the two questions. Are there any more questions from anybody? Any questions, comments? Okay, so if not, then we will finish this lecture. And at the end, I would like to tell you that do please attend these discussions. Interannotator agreement is very important for us when we deal with data. Okay, and in today's world of AI machine learning, we cannot ignore those discussions, and these are really very empowering. And the final statement, absolutely final statement, we are trying to connect the two concepts of interannotator agreement and hypothesis testing. Do revise the discussions on hypothesis testing. You will appreciate interannotator agreement better that way. Okay, thank you. And I'll stop now.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
So